This lecture is on memory. This is at the end of an introductory course in computer architecture and high-tech fundamentals, where we've already reviewed most of these topics. This is extra information, supportive information. So this is about memory and a little bit about operating systems also. Firstly, ENIAC, 1945, University of Pennsylvania. One of the very first computers of any kind. Had only a small number of registers, about 20 for storage, and implemented these with the same basic vacuum tubes. Perhaps you've seen me show you those in the laboratory. Each one is essentially a switch, a transistor in itself. And this computer was used for actually calculating trajectories for cannon fire in World War II. There's a couple different types of technologies they talk about in here, so I'm just highlighting in red the ones that I'd like the students to know. Also, because I'm a former IBMer, and also because IBM pretty much invented most of the technology we see in a lot of computing these days, we should reference IBM. So while registers were built out of transistorized memory in the 1960s, so we're going to solid state then, the IBM computers used transistorized memory for microcode, store, and caches. So that's if you had a course on designing the CPU and the control unit, the microcode for the sequencer in there. And then caches. So, in the 1960s and early 70s, IBM is coming up with cache designs. So it's not a new thing. Building main memory out of transistors remained prohibitively expensive at the time. So it's the same idea as today, with the faster, smaller, more expensive memory doing some of the calculations. And so this is the beginning of DRAM, dynamic RAM, which we've learned about in other lectures. And the package that they come in, we've talked about this in the introductory course, the DIMM, the dual inline memory module, versus SIMM, single inline memory module. It has more to do with the way the connectors are aligned. And there's a picture of a SIMM there. Not that different from what you see now in PCs with the DIMMs, just there's two sets of connectors on the bottom. And also, we've spoken of virtual memory, where the CPU and the operating system and the programmers all assume a larger address space than the physical memory. And so you have virtual address translations every time you're accessing real memory. And so this is an IBM thing in 1972, a long time ago. Then in the 1990s, I believe we've already talked about RISC. So several RISC, reduced instruction set computers or devices made the transition from 32 to 64. So I was a little bit instrumental in that at IBM. We switched from 32-bit machines to 64-bit to large-scale multiprocessor systems, 20 chips per board. 18 of them were for general processing, 2 were for dedicated communication channels with a separate instruction set and optical channels. And then all those boards fit into a big rack, up to 512 in the System 390. So we were switching to 64-bit at that time. We had the architecture already specified, but we didn't have prototype machines built yet, so we simulated we simulated 64-bit architecture on 32-bit machines to test the prototype ideas before ever making the actual machinery. Then down below here, you see 1965 tunnel diode memory, the fastest form memory available at the time. So using this extra, this expensive extra little memory in the cache out of this type of technology. IBM started a project that led to the first commercial computer with a cache, the 360/85. So I wasn't in high tech at that time other than building buildings for high tech companies in Texas and California, since my undergrad education is architectural engineering and then urban design and then architecture and engineering of large buildings before I went back for my master's and PhD. But however, I built two IBM 360 raised floor computer rooms and had to know something about what they were doing to set that up. Gibson, this person at IBM, recognized that memory accessing behavior would have a significant impact on performance. He described how to measure program behavior and cache behavior and showed that the miss rate varies between programs. Using a simple sample of 20 programs, each with 3 million references, which was a lot back then, he analyzed the effectiveness of caches using average memory access times as the performance metric. And then this whole notion of caching now, we've talked about anticipating what you need. You can apply to other things, in operating systems, networks, databases, compilers, to name a few. We cache virtual address translations. We cache branch target address formations. Anytime you're anticipating something you need ahead of time, is this general principle that was developed here with the initial caches with IBM. Protection mechanisms. So when you have a very large address space, you can put privileged access to certain sections. So we did that inside of IBM. Actually, when we went from a 32-bit operating system when I was there to 64, suddenly there's a tremendously huge space, right? So tremendously more. So 2 to the 30 is like 2 to the 32 times 2 to the 32. That's what 2 to the 64 is, and 2 to the 30. We learned from memorizing our orders of magnitude. 2 to the 10 is a kilo, about a kilo, 1,000. 2 to the 20 is meg, about a million, and 2 to the 30 is a gig, about a billion. So 2 to the 30 times 2 to the 30 is a billion times a billion. So suddenly you have a billion times more space, a billion times more space. So everybody just spreading out and having privileged access. You give everybody whatever they want. And so now IBM, again, first computer with virtual memory back in late 1967. Now there's another thing you can do that's a little bit different, but the same general thing of separating memory. When we talk about virtual memory, initially it's that the address space is bigger than the real memory, the virtual address, and you have to do a translation. There's also a thing called a virtual machine. So in IBM, we could partition the machine so that it could act as multiple computers at the same time, doing completely independent things, or correlated if you like. Those are virtual machines. A little different than how we've defined a virtual address, but very much related. Now, a very brief overview of operating systems. So in 1961, first time-sharing system. So if you know about operating systems from other courses, you spawn a whole bunch of tasks, you do things, multiple threads, multiple things happening at the same time. You schedule operations, things in the background, the foreground. So, time sharing And this is 1961 at MIT. And an interesting little quote here. Classical book about lessons learned from developing an operating system for IBM mainframe. The Mythical Man Month. When one is designing the successor to a relatively small, elegant, and successful system, there is a tendency to become grandiose in one's success and design an elephantine, feature-laden monstrosity. So that's a telling statement that you see happen in a number of places. I mean, you can certainly apply that a number of things, even outside of computing, where you got something good and elegant, and then people want to build more, and the next thing you know, it's not quite the same thing. And that happened with RISC versus CISC processors. We realized, well, whoops, we went a little too far. Nobody's actually using all these features, and it's creating a slowdown in the overall performance to have those features. So the cost benefit wasn't there. So next year, MIT, General Electric, and later Bell Labs. If you don't know Bell Labs, the telephone company used to be AT&T, and that was it. It was a monopoly, and there were, and so they had the ability to do great research because they were a monopoly. Not all monopolies do that, but they did, and so Bell Labs was a great research thing. It got broken up because of antitrust laws, broken up in all the baby bells, and then Lucent Technology came out of it, which what used to be Bell Labs. Still very good, but not quite the powerhouse Bell Labs was when it was funded fully by a monopoly. So anyway, Bell Labs, they all tried to build an economical and useful system despite a great deal of time and money. They did not succeed. Now Berkeley, UC Berkeley, University of California, Berkeley, was building their own time-sharing system around about this time. And then eventually at Bell Labs in 1971, Unix, a beautiful system, elegant operating system, and I use that quite a bit in Sun workstations and research labs. At IBM, we had our own version called AIX, and then later you're probably familiar with Linux. Some more details here you can read through. I haven't highlighted anything in particular, but if you want to know the whole history, you can take a look at that. Now here I highlighted quite a bit. I'll summarize it. So the first computer is Alto. Had a graphic display, Windows, client-server computing, Ethernet, print services. It inspired the Macintosh, right? The first, the Apple, the beginning of Apple computers, and what was a successor to Apple II. Actually, the Apple was the first, and then the Macintosh came after. IBM, existing at this time and long before, many decades before, had long been interested in selling to the home, to the consumer. They had been interested, but I could tell you firsthand, asking senior management when I was inside of IBM, where did they go wrong losing this whole market of the PC, and they assured me that it was never more than 10% of the revenue of the company. Most of the revenue of the company is making their own computers, large-scale systems, enterprise systems, and supercomputers, and not focusing on putting together other people's parts, which the PC was initially by IBM. So anyway, IBM does get in the marketplace at one time, even though they're used to doing everything themselves, and they put in a cheap little Intel processor at the time, and low cost. They visited Microsoft to see what this little small company, Microsoft at the time, would be willing to sell their popular BASIC interpreter, and asked for recommendations for an operating system. Gates, that's Bill Gates, volunteered that Microsoft, he was very young then, could deliver both an interpreter and an operating system as long as they were paid a royalty instead of a flat fee. That was a brilliant move. That's how he made his first bunch of millions. IBM agreed, and so you can read the rest there. Essentially, they packaged quite a bit, and eventually 500,000 copies. And they didn't, and Bill Gates didn't actually write that. He just repackaged an existing operating system and made that MS-DOS. And so that was the beginning. And once he had the first bunch of millions, then it was just momentum after that. Now I believe he's the wealthiest man in the world, with a net wealth exceeding most of, or many, if not most, of the gross domestic products of entire countries in the United States, or in the world, not the United States. A couple more comments here. The Macintosh was announced in 1984, so that the Apple had been out before that, and the IBM PC was competing around then. So I bought my first IBM PC. I actually bought the very first clone with compact of an IBM PC in 1983, and I used it to start an estimating business in the building industry. Programmed my HP calculator to do quantity takeoffs and then feed it into my spreadsheets, beta tested spreadsheets before Excel, long before Excel, before Lotus. I was a beta tester for SuperCalc, and then I had a friend at the University of Pennsylvania, who was about my age, we were 20 years old, who was testing VisiCalc. He sent me that, and I spun that into helping me get jobs with real estate developers building high-tech buildings. Anyway, story for another time. The popularity of the PC led to a desire for a Unix that ran on it. So here comes Linux, and most of you probably know Linux today. Linux popularized open source development, as we know it today, with much software getting hundreds of volunteers to test releases and add new features. That's the key thing. So kind of a crowdsourced intelligence, the design intelligence of many people. And some references for further reading if you would like.